Hi, I had noticed after we went through our lesson and you guys left that we still had a part of the notes left to do. So what I'm going to do is I'm going to put it here online, and then if some of you see this, great. If not, we'll talk about it some, the next time we get together. So we talked so far about when something was dropped, and we'd also talked about when an object had an initial velocity that we were working with. If it's not dropped, if it was thrown or vaulted a direction. Well, there's one more model or one more twist that can get thrown our way, and it's called when we have meters per second instead of feet. Now, the equation itself, as you can see, is just the same. The only difference is going to be now, instead of our negative 16 t squared, now it's negative 4.9 to adjust for meters. So for instance, we have John throwing a water balloon upward from initial height at 20 meters at an initial velocity of 10 meters per second. Write the equation describing the relation between the balloon's height above the ground and time. Now, like we said before, that just means we're going to keep our equation, and we're going to take our initial height, plug it in for h of 0, our initial velocity, plug it in for v sub 0, and everything else is going to stay the same. So as far as that goes, not much is changing. And that's going to be the same basically for all of this. So when I go to graph this now, though, again, let's look to see what we want to do here. So negative 4.9, again, we use the x for our t. We go ahead and graph it. Now, what's the height of the balloon after 2 seconds? Now, we've spoken before about that my time is like my x value. Now, I could do a couple of things. I could just go to the chart, find it there, find out that it'd be 20.4 meters. I could, if I wanted to do it graphically, just hit trace, and I can find the y value of any x value I want just by pressing in trace and then my x value 2. There's the 20.4. Either of those would work. So if I want to find the height, that might be a little way that's going to be faster for me. However, how long did it take for the balloon to reach the ground? Again, now I'm looking for a 0. So I go back, I do my second trace. Okay, I'm looking for a 0. And like I said before, this negative one I'm not really interested in because I can't have negative time. So that's the one I'm interested in. So I'll scroll, there it is. And again, like we said before, as long as my cursor is somewhere above, in this case, the x-axis, it's to the left of the point I'm trying to trap. So I can hit enter. Right click until I'm below the axis. Again, then I'm trapping my central point in. And we'll go back a little towards it. And we find out it took about 3.28 seconds for that balloon to reach the ground. And that's, again, how all of these work. If I'm looking for time, typically I'm going to be looking for zeros. If I'm going to be looking for heights, I might be looking for a maximum, or I might have a specific value that I'm looking for. So let's kind of keep looking here. Chizuko threw a stone upward at a speed of 10 meters per second while standing on a cliff 40 meters above the ground. Okay, same idea. Write an equation describing the relation. Typically, my first term doesn't change. My initial velocity, once again, happens to be 10. And this time I'm on a meter 40 meters above the ground. So similarly to the two questions we just answered in the last one, the only real difference here looks to be that now it's 40 instead. So I can look at my graph. What's the height of the stone after 3 seconds? Again, I can look at my chart, 25.9 meters. If I wanted to, I also could just hit trace and the x value that I'm looking for. Again, I can get my height that way. X is time, y is height. How long before the stone hits the ground? Again, this is the 0 we want. So we'll go for 0. There's my cursor guy. He's above and to the left. More importantly, to the left. Here he is to the right, and we're trapping our 0 in. And we find out it's going to be a little over 4 seconds before that hits the ground. So again, technically now that we've brought meters into play, what's happened is we now have 4 possible formulas that we can use. Okay, if we drop it, if it's feet we use -16, if it's meters we use -4.9. Launched or thrown, we have our initial velocity as our middle term, but again, the -16 and the -4.9 still come into play. So what our job will be is to figure out each time which one of them to use. But again, the key here is it dropped or launched? And then my second thing is it in meters or feet? Okay, those are the 2 decisions you have to make when you start. So for instance, on number 10, in an engineering school, students are challenged to design a container that prevents an egg from breaking when dropped from a height of 50 feet. Write an equation giving the container's height in feet above the ground after t seconds. Now again, we notice dropped, we notice feet. So we're like, okay, dropped in feet, we're going to use this guy. So h equals -16t squared plus my initial height, 50. That's all I need. How long does it take the container to hit the ground? Again, we're trying to figure out when that 0 is going to come. And like we'd done in class, you could do this algebraically. You could get the 50 to the other side and use a root, and that's fine if you want to. But since we're doing so much with the calculator here, I really like you to be able to do it both ways. And most of you are so good with that. Let's see how this one would go. So if we clear this out, -16x squared, because again, we don't have a t available. And I'm looking here to see how long does it take to hit the ground. What's my 0? So again, we're going to use second trace to get our 0. We'll keep scrolling up there with my cursor guy. Okay, above, enter, below, because again I'm trying to trap that 0, enter. And it looks like it's going to take about 1.77 seconds. But again, with all of these, kind of do your checklist here of what you're trying to accomplish. Ball's thrown upward from an initial height of 20 meters, initial velocity, so I know it's going to be one of these two, of 10 meters, so it's going to be this one per second. Write an equation for the height of the ball. H equals -4.9 t squared. My initial velocity is 10 meters per second, and I'm doing this from a height of 20. So there's my equation. What's the maximum height? Okay, so when I type this in, clear that out, -4.9x squared plus 10x plus 20. Now, if I'm looking for a maximum we talked about before, how can I get this where I can actually see it if I want to do that? Well, it looks like the window just needs to rise some. So let's try raising the y value to 40. Okay, now I can see it. Again, I'm not looking for the 0 this time. I don't want 2, I want the maximum. So the maximum, again, I'm trying to trap my vertex in here. So anywhere over to the left, I can have my cursor and hit enter. Anywhere to the right, have my cursor, I can hit enter. And then approximate. Now again, what is the maximum height? That's my y value. When does it occur? That's my x. So it's about 1.02 seconds, and it's going to be about 25.1 meters. And I can get both of those. And then finally, when does the ball hit the ground? We're back to doing zeros again. Again, -1 doesn't matter. Anywhere above is for my left, because again, my cursor, here's my point. I'm to the left of it. Hit enter. Get below, because again, that's to the right of my point. Hit enter, and one more time. So it's going to take about 3.28 seconds for the ball to hit the ground. So this will be available to you. Sorry I can't have it going in class without a computer. But we'll talk about this on Tuesday if we need to, and hopefully you'll see this if you need it before then.